how good these machine learning algorithms are on unknown test sets. We want to analyze this question theoretically. We are interested in this question, how many training samples we need to achieve small error on test problems. And another important question is, what's the smallest possible error that we can achieve with these algorithms? Meanwhile, Fish, can you figure out how to turn that off? Let's see if we find a way. Okay, and these are those kind of questions that learning theory studies. Yay. Is it better? Yep, good. And it's very dark, so I cannot see you well. So you can sleep. So to answer these questions, we have to discuss some definitions of risk and loss. We already did that in the first lecture, but now we will be more formal. And so we will define loss and risk functions, and then we will discuss the concept of empirical risk minimization. We will discuss underfitting and overfitting and see how empirical risk minimization can be used in classification and regression. We will focus on classification mostly. All right, so in this learning theory section, we will discuss supervised learning setup, which is this. We have a data set, the training data, which are pairs, x1, y1, x, and yn. So x is your input, y is the output. And we have some test data set as well. For example, in this data set, the first endpoint is the training data, and the next endpoint is my test data. And we assume that the inputs are coming from a d-dimensional feature space, and the labels are real numbers. And we assume that there's a joint distribution of the features x and labels y. So there's a joint distribution of x and y, and we assume that the feature vectors x, they are samples from some distribution px, which I just denote with mu, and the class labels are sampled from a conditional distribution given x. In regression problem, of course, the labels are, say, intervals a, b. In classification, they could be like just 0 and 1. All right, if we want to study how well our algorithms work, then we will need a loss function L, which is defined on xy pairs, and the algorithm, given features x, the algorithm predicts f of x, and we want to compare f of x with y. And our goal is that we want this loss to be as small as possible on the test data set. Okay, in classification, we are interested in this loss that's called classification loss or 0-1 loss, which has value 1 if y, the true class label, is not the predicted class label, and 0 if they are the same. In regression, we might use the L2 loss or the L1 loss, right? So we all know these kind of things so far, right? We already studied the squared loss, the L2 loss. We know the L1 loss. When we discuss support vector regression, we discuss the epsilon insensitive loss. And in robust regression, sometimes people use the Huber's robust loss. So everything is known so far, right? There was nothing new. Okay, so this was the loss. We will need the definition of so-called risk function. And the risk is defined as the expected value of the loss on your data. So as we discussed, the xy pairs have a joint distribution pxy, and we take the expected value of your loss with respect to this distribution your data is coming from. So the risk is just the expected loss. Okay, so why do we care about this risk?
That's what you want to minimize.
So our goal, my goal is to do well on the test set. How is it related to that?
That's the same expected.
No, I have a test set, right? X n plus 1 y n plus 1 x m y m. That's what I care about. I want.
Do you see? You see the test set?
Right. So.
I guess because you're doing expectation and not MLU or something like that, you can kind of account for any, like you're trying to predict the worst thing that could happen.
Right. So I care about the performance on a test set, right? But what happens is that the loss on the test set, the average loss, is converging to the risk.
Are you given the test set or not?
So you have let's discuss this. So for example, what happens if the test set is given? But you have the test instances, but not the features, right? You have m of those. X n plus 1, x n plus 2, x n plus m. I want my algorithm to work well on these instances. Right? So that will be really the average loss that I really care about.
Yeah, but that's when you don't have. I mean, if you have, so you probably could do something better. If you know that if you know what you would be tested.
I agree that you could probably do something better, but I'm just saying that if you have these features, my point is that this guy will be close to this point if the features are known. If the features are not known, then indeed I cannot do anything else, just studying the expected loss, because that's what I care about. Okay, so but the point is that we will focus on analyzing the risk. Does it make sense? So I understand indeed, if I have the features, all the features, then I might somehow exploit the structure in that's called semi-supervised learning. But to keep our life simple, so this is what I care about. And the point is that the expected risk will be close to this empirical loss if the test set is large enough. Okay, so notation that the risk belonging to the loss and the joint distribution of x and y is defined as the expected loss x, y, and f of x.
So are we assuming here that we learn f from the training data?
Okay, so you can define the risk for any function f. I give you a function, this is its risk.
So this does not have to be the best one. So
yeah, for any function, any deterministic function, I can calculate this risk, right? And of course, what we are going to do, that you have a training set. And from the training set, you learn a function f. And you can calculate what will be the expected value of this loss, where you learn this function from your training data.
And you assume that you're giving the distribution.
I don't assume. I'm just saying that this is a theoretical thing, right? This is what I care about. But of course, the algorithm doesn't have access to this distribution. The algorithm has access only to the training data. All right, so this is the risk. The risk is the expected loss. If we use the classification loss in classification problems, then the risk will just become the expected value of this 0, 1 loss, which will be the probability that f of x is not y. Okay. For L2 loss, which is defined by y minus fx squared, the risk of this L2 loss will be the expected value of y minus f of x squared for any given function f. Okay, and now comes this question that, so I can define the risk for any given function f. But what I want is that I want my learning algorithm to learn this function f from the training data. Because of that, this function f will not be a deterministic quantity anymore. It will be a random variable, which depends on your training data. For different training data, you would see different function f. Okay? And because of that, this risk will be a random variable as well. Because for different training data, you will see different values of the risk. So we have to deal with random variables and convergence of random variables. And now here's my question. What do we mean on convergence of random variables? So do we know? So what do I mean when I say a random series of random variables converge to a quantity?
Depends. We usually mean that convergence distribution. That's the weakest sense you can.
Right. So what kind of convergence notions we know?
Almost surely.
Almost surely. Who doesn't know almost surely convergence? So everyone knows almost surely convergence. Who knows almost surely convergence? It's, I don't know. If I sum these hands and the whole class is just not the whole. So there's almost surely convergence. What other convergences do we know?
L1 and L2 convergence.
Okay, so convergence in L1, L2, or LP. Convergence in probability. So that's like the L2.
Distribution.
And convergence in distribution, right? So these are the most important convergence that we need. So what follows? We will use the convergence in probability. And so the definition is that if you have a series of random variables Zn, which defined in an abstract space. So you can always think of random variables as functions, right? That are defined in an abstract omega space. And the definition is that for each epsilon, so we say that the series of random variables Zn converges to random variable Z in probability if for all epsilon bigger than 0, the limit of these quantities converge to 0. Right? So the probability that Zn minus Z absolute value is bigger than epsilon, that's converging to 0. And this is just a graphical notation of this convergence that I want to demonstrate what it means that Z1, Z2, Z3, and so on, Zn converging to Z. I plotted Z1 omega minus Z omega. So again, Z, when I say Z random variable, you can always think of this as a function in an omega abstract space. So this is how you define random variables, right? So when I say that a random variable is a function, you know what I mean on that? Or, okay. So I just plotted Z1 minus Z omega, Z2 minus Z omega absolute value, Z3 minus Z omega absolute value. And for each epsilon, so this is epsilon, and this red line shows the value at the fixed epsilon. So the probability that, say, Z3 omega minus Z omega bigger than epsilon, that is this region here, these probabilities have to converge to 0. So that's what it means. So it's like a uniform convergence.
The notation is an arrow with a P over?
Notation?
An arrow and a P over, that's how you...
Here? Yeah, so this is the notation that Zn is converging to Z in probability. So there's a P there. If it's almost surely, there would be a dot S there. So almost surely, or if it's in distribution, there would be a D there. Okay, but so this is the definition we will mean on that Zn converging to Z in probability. All right, so again, the risk for any function f is defined as the expected loss. And we want to find that function that minimizes this risk among all possible functions. And in the first class, we mentioned that that's the so-called base risk. So the base risk is the infimum of these risks when it's minimized over all possible functions. And I will denote this with R star, L, P. Okay, and our goal is that using the training data, D, using this training data, learn a function f of D whose true risk will be as close to the base risk as possible. It makes sense, right? So the base risk is defined by this. That minimizes the risk among all possible functions. I have a training data. From the training data, I can learn a function fd. That function fd will have a true risk, and I want this true risk to be close to this guy. And again, what I mean on close to this, that's a good question, because this is a real number, fixed real number, and these are random variables. So I want these random variables somehow be close to this fixed number. Yes?
Sorry, I'm not sure why the risk is random. Is it the empirical expectation?
So the base risk is not random, right?
Yeah, but
This guy, it depends on your training data. The training data is random. F of D, that's a random function.
oh, your function is random.
Yes, f of D is a random function because it depends on your training data. If you get different training data, your function would be different. Okay, so
So, do you look for a function before you see the data or after you see the data?
so you get your training data, that's a random data. You learn, you see that, and then you learn your function f of D from this training
It's
data.
a fixed function. It's not dependent. I mean, you already have the data, so it's...
But what you want to say is that you don't want to depend on that training data that much. So you want to remove this randomness in that sense that, for example, if you usually you can collect like more training points, or for example, think of images. Okay, your training data can be images. I don't know. You want to do a face detection, you collect some faces. Sure, if you fix those faces, they are fixed now, but you might assume that someone collected other faces for you, right? So generally, it's good to think of this as your training data. They are just random points, and this was our assumption actually, that we assume that X, your training data, is sampled from a distribution Px, and similarly, your test points are sampled from the same distribution Px. So we assume that our training data, they are just random realizations of this distribution P of X. Okay, so these could be like images of faces that you collected, but you could have collected other images of faces as well. You still want your algorithm to work on other images. So you don't want your algorithm just to work on this particular training set. You want your algorithm to work on any sample set from this distribution P of X. Does it make sense?
So actually, what do you use your training set for choosing?
You have the training set, and from that training set, you will learn a function f of D that will be, for example, your classification function. So I want to say do a face classification problem. I collect lots of images of faces. That's my training set. and from the training set, which is a random set because I collected random images from the internet of faces, the algorithm builds a classifier that's f of d, which is a random function because my training set was a random function as well. Okay? And we will say that a learning method, like, I don't know, support vector machine method, k-nearest neighbor classifiers, Gaussian processes, so whatever learning method you have, is universally consistent if for all distributions, pxy, the risk of your, say, classifier converges in probability to the base risk. Okay, so the base risk, that's the thing, that's the best you can hope for. Right? Because that minimizes your risk among all possible functions. That's a theoretical thing. We can never know this, but what we want is we want our algorithm to converge to this guy. F of d, that depends on our training set. So this risk is a random variable, and what we want is that this random variable in probability to converge to the base risk. If we achieve that we are good, because that's the best thing we can hope for. Is it clear? Any questions? Okay, so you have your training set, which is a random sample set from a distribution of pxy. You learn a function from your training set that will be a random function. That random function has a risk, which is a random variable, and we want this random variable to converge to the base risk as you increase the training set n. Okay, so that's the other thing why I cannot say that the training set is given, because I want to study this convergence as you have larger and larger training set, how the algorithm behaves. And on larger and larger training set, I mean that I have more samples from this joint distribution pxy. Okay, so the good thing is this Stone's theorem, who in 1977 proved that many classification and regression algorithms are universally consistent for certain loss functions under certain conditions, like the k-nearest neighbor classifier, kernel regression, support vector machines, and it didn't prove for Gaussian processes, but Gaussian processes as well. They are all universally consistent in that sense under certain conditions. So if you have more and more training data, the algorithm, the risk of your algorithm will converge to the base risk. And then we are done. That's what we wanted, right? So we can go home. Because machine learning is solved. Base risk is the best theoretical thing you can hope for, and these algorithms all converge for that. You just have to have large enough training set.
Not enough training sets and infinite processing power.
Right, so the slight missing detail here is that it doesn't talk about the convergence rates. It just says that if we have large enough training set, then the risk of your algorithm will be close to the base risk.
You still don't necessarily know when you've converged.
Right, so you don't know when you will get there. It might take very long time, and that's not a good news for us, right? So what's worse is de Vroij's theorem, which is called no-free lunch theorem. He said that if you fix any convergence rate an, could be arbitrarily slow, you can always find a pxy distribution such that the convergence rate of your learning method for this pxy distribution will be slower than your rate. So what it means that the learning rate can be arbitrarily slow. Okay, so the risk of your function that your algorithm learns can converge to the base risk arbitrarily slowly. You can always construct difficult pxy distributions. So you tell me a convergence rate, I can construct pxy distribution such that the convergence of the risk of your algorithm to the base risk will be slower than the predefined rate you gave to me. Does it make sense?
But if you give the same data points over and over again, does that count toward this theorem? So I guess implicitly we have to make an assumption that
Right. So this, what this theorem says, that I can construct a difficult pxy distribution. If your pxy distribution is already given, then this theorem doesn't apply.
it's kind of trivial. I mean, if you just, for example, give the exactly same points as n plus 1 is the same as n, xn plus 1 is the same as x.
Okay, so the other thing, so we assume that the samples are always IID. So the
You
x
sample at random.
and independently from the previous samples. Okay, so I'm not studying time series. The sample points are independent from the previous.
But you can always cook up some distribution like that, right? Which samples actually the exactly same points that you have sampled in the last 10 one. So you really don't learn anything about the process.
Sure, that's true, but that would be still like. So in our framework, I assume that the sampling process is IID, which means that the n plus 1 sample will be independent from the previous sample points.
But they may still charge the same discrete points. You may actually get one of them anyway, as you move on. As in the discrete.
Sure, right, yes. But
Because this theorem does not prevent me from just playing with any p, so I can just come up with any p. So it says that you can come up with some p which makes learning impossible in a sense.
yes, so this theorem covers that. So it's not a problem if you go back to the same xy pairs, because that will still tell you something about pxy at the end, right? So you can calculate the histogram of xy's, and the histogram will converge to this true pxy. So you could still learn. So it's yes.
Is there anything on the other direction helpful? Like, not given a learning algorithm, I can really cook up something bad, but given P, is it possible then to cook up?
Yeah, so that's people also study those.
Is it?
And
What's the?
there are hardness theorems for that one as well. So I can give you references for that. All right, so this is the bad news. So what people do is that we restrict the possible distributions. So we might say that the problems we care about, they cannot be arbitrary distributions. But for example, we care only about those pxy distributions where P has certain smoothness properties, like D times differentiable or something, or Hölder continuous, or yes?
How, existence theorems in math could be like really non-definable.
Mhm.
Definable is
Oh, so with this one, the proofs are constructive. So they really construct bad examples. And if you go, will you attend Larry Wasserman's statistical learning theory class? Usually he tell you the recipe how to cook bad examples for certain classification or regression problems. And I can send you some papers on it if you are interested. All right. So the learning rate can be arbitrary. So what can we do now? All right. So just one more thing. So what we mean on learning rate, I haven't defined that yet formally. So this is a random. These are random variables. We know what we mean on that these random variables converge in probability to this quantity. We define that. But what we mean on the rate of convergence, that's not defined yet. So I want to ask, do we know what we mean on rate of convergence in probability? So if that was a midterm question, write down the rate of convergence in probability, then everyone would be okay, or no? So okay. So by the way, I uploaded, I think, like 50 slides on stochastic convergences. So you might want to look at that on the class website. But this is what we mean on probability. So we know the little o and big O notations, right, for deterministic quantities. So for stochastic variables, you can define little o p and big O p. It means that little o in probability and big O in probability. And we say that xn converges to 0 with rate an using little op notation if xn divided by an converges to 0 in probability. So this is the generalization of the little o notation. That so it's exactly the same for deterministic quantities, just you wouldn't have this p here, right? So we say that xn is little op an if xn divided by an is converging to 0 in probability because these are random variables. So an is a fixed series. And the big O notation is that we say that xn converges to 0 with rate an using this big O notation if xn divided by an is big O p1, where big O p1 is defined like this, that we say that big O p1 just means that the series of xn is stochastically bounded, where stochastically bounded means that for all epsilon fixed number, exists a threshold number m epsilon, which is finite, such that the probability that xn bigger in absolute value, that epsilon is bigger than m is less than epsilon. Okay, so what does that mean? For example, a Gaussian distribution that's stochastically bounded. So it's not bounded, right? Because the Gaussian distribution can have any big value. But it's stochastically bounded because for any epsilon, you can find, so this is a Gaussian distribution. For any epsilon, I can find a large enough m such that the probability that the Gaussian random variable is bigger than m in absolute value, this guy can be small. Okay, so the Gaussian distribution is not bounded, but stochastically bounded. And for example, the central limit theorem says that the empirical average, so you have a series of random variables, x1, x2, xn, which has mean mu, and they are IID, then we know that xn bar is converging to mu, right? And the central limit theorem says that square root n times xn bar minus mu, that would converge to a Gaussian distribution. Right? So we know the central limit theorem, right? That square root n times the empirical mean minus the mean, that's converging to a Gaussian distribution. So informally, that just means that xn bar, the empirical average, minus mu is big O p1 over square root of n, because if you multiply both sides by square root of n, it just means that square root of n times xn bar minus mu is big O1 in P, so it's stochastically bounded. Okay, so xn bar minus mu has this rate, but xn bar itself doesn't have this rate if mu is not 0. Because if you multiply xn bar, so just you have a random variable which has some mean mu, which is not 0, then square root of n times xn bar will have larger and larger mean value, so it's stochastically not bounded. Okay? All right, so so this is just the background on what we mean on stochastic convergence and convergence rate. All right, so again, we have a loss. We define the risk for any function f. The base risk is the infimum of the risk where we minimize over all possible functions. And of course, we don't know p, this p distribution of x and y's in practice. We just have training examples. So we don't know p, and that's because of that, for any given function f, we don't know the risk of that function. Right? So you have a classifier with function f. Because we don't know pxy, we don't know the risk of that classifier. So what we can do instead, we don't know p, but we can use the empirical risk, which is just the empirical average of the losses in my training set. So in my training set, there are xi, yi pairs. For a function f, I can calculate the loss. For example, with classification loss, this would be 1 if I misclassify yi using function f at instance xi. So this is the empirical risk. And the law of large numbers says that for any fixed f, the empirical risk is converging to the true risk for any fixed f. Our goal is to minimize the risk for all possible f's. But I don't know the risks. So maybe one approach could be, let's just minimize the empirical risk for all function f.
So what I'm saying is that if you always solve the empirical minimizer for the minimizer of the empirical risk, then you're going to be universally consistent.
I didn't say that.
No, but isn't it that? Because you're saying that if you minimize over the empirical risk,
right,
then you're going to converge to the base risk. Isn't that the same as?
Right. So if I minimize the risk for all possible f function, that would be the base risk. That's clear, right? So the minima
Okay. Yeah.
R of min of R of f, that would be R star for all possible function f. The problem is that my algorithm doesn't have access to R. We have access to Rn or R hat n, the empirical risk. So instead of minimizing this, I can just try to minimize this. But that's a terrible idea. Why? So you want to minimize the empirical risk over all possible functions. You want to minimize the empirical risk on your training data. And if you minimize over all possible functions, you can always achieve minimum error on your training data. But it doesn't mean that you will be good on your test set, right? So I tried to construct this example to demonstrate this, that this is a classification problem, and this is how the samples are generated, that if you are, so this is x, this is y, and the probability of y is 1 given x is 0, so you are here, is 90%. So on this side, with 90%, the class label would be +1, with 10% it would be -1. On this side, with 90%, the class label would be -1. And with 10%, the class label would be +1. The optimal base classifier in this case, it's easy to prove that you have to say that the predicted class label is 1 if x is bigger than 0, and the predicted class label is -1 if x is smaller than 0. And the base risk, so the risk of this optimal classifier, would be the probability that y is not f star x, and that would be 10%. Okay, so with 10%, you would make some error. So that's the base risk. If this is your training set, and you minimize the risk on this training set where you consider all possible functions, then it would look, your function might look like just this. So f of x, here is the sign of, I just used, I don't know, n order thresholded polynomials. And then, of course, you can always fit a polynomial that would go through these problems. And
goes to infinity.
Yeah, right? So the risk, the empirical risk here would be 0 on your training set. But the true risk of this function would be 0.5. So it's just a random guess. So on test set, you would be terribly bad. But as we discussed, the base risk of this problem is 0.1. So if you just minimize over all possible functions, that's not a good idea. So that's called overfitting. Yes?
Is it possible that you get more than one function that has the same minimal risk?
Right. So on the training set, Yes, so you could just change these functions a tiny bit, right? So there are lots of infinite number of functions where the empirical risk is 0.
So the question is, how do you pick one?
Right. So the problem is that you don't even want your empirical risk necessarily to be 0 because you might overfit your problem. So what we are going to do, that instead of considering all possible functions, we want to consider only simple functions to avoid overfitting.
Would you change this maximum risk max?
So that's a different different problem. So let's discuss that after class, right? So the problem. So what I just wanted to show that if we minimize the empirical risk over all possible functions, that's a bad idea. That's what we do for calculating the base risk. You want to minimize the true risk over all possible functions, but we cannot minimize the empirical risk over all possible functions. All right, so this is just another demonstration of the same thing. That, for example, these are sample points from xi pairs. So the points are generated that are, so this is a regression function, this is the true regression function, and these are just my noisy observations. If I fit a first order polynomial, then that would look like this. A second order polynomial on this data would look like this. A quadratic polynomial would look like this. A sixth order polynomial would look like this. So on the training set, I have smaller and smaller errors. But outside of my training domain, I would make more errors, and the test errors would be huge as we increase the order.
What is the function?
I just drew a function.
Where?
Yeah, whatever function. All right, so as you fit more and more complex models, your training error is going down, but the test error might increase. So to avoid this, what we are going to do, that instead of minimizing over all possible functions, from now on in empirical risk minimization, we will minimize over just a predefined function set, which is I denote with calligraphic f. So that's the empirical risk minimization problem. Find f of fn star, where we just minimize over functions in a function class f. That function class f could be first order polynomials, second order polynomials, neural networks with 5 layers, and so on.
And you still know nothing about the real function.
I know nothing about the real function, but
It doesn't have to be in this type.
it doesn't even have to be in this functions class f. Okay? Still, the empirical risk minimization principle is this, that you choose a function class f, and you just minimize the empirical risk over that function class f, even if your true function that would lead to the base risk that's outside of this function class. Okay, so this is the empirical risk minimization problem. Does it make sense so far? So you fix a function class f, and you minimize the empirical risk over the all functions in this function class. Okay, so the notation will be this, that r star f will be the minimum of the risk, true risk, in this function class f. Again, it's just a theoretical thing. I don't have access to this because I cannot calculate the true risk. And the empirical risk in this function class f will be this quantity. You minimize over all functions in this function class, you minimize the empirical risk in this function class. Okay, so from now on, this will be the empirical risk R hat. So I use n here to denote that in the training set I have n points, and I use f to show that I'm optimizing in this function class f. Okay, so this is my empirical risk, and this is the risk in this function class. So one thing I want the risk that I can calculate in this function class to be as close as to base risk as possible, because ideally I want to get to the base risk, right? I fix a function class. This function class should be large enough such that the risk in this function class, the optimal risk, should be close to the base risk. But I cannot consider all possible functions either, because we discussed that's a bad idea. So what people do sometimes in practice, that as you increase the training set size, you increase the number of functions that you would consider. So let fn mean a predefined function class when your the training size is n. For example, but just an example, let fn be n-order polynomials. So as you have more and more training points, you would increase the complexity of the functions that you would consider. Because you increase the size of the functions, this true risk, the risk in this function class would converge to the base risk. And that's called structural risk minimization. And there's a huge literature of this, how you need to consider larger and larger function classes. Okay, so this is a decomposition that quite often we will do. So for any given function f, we can talk about the risk of that function. And I want my algorithm to find a function such that the risk of this function is as close to the base risk as possible. So this is the base risk. Sometimes I will just use r star to denote this base risk. For a fixed function, it has a risk. And I decompose this difference using these two terms. So this is r of f minus the infimum over all functions in the predefined function class. And this term is called estimation error. So how far is the risk of the fixed function f from the best risk that you could get in your predefined function class f? That's called estimation error. And there is another term called approximation error, this quantity, which is how far is the best risk achievable in your function class f, how far is that from the base risk. So usually we decompose this quantity you care about to these terms, estimation error and approximation error, and of course you want both to be as small as possible. Any questions? Yes?
So you still don't know the true risk, so how can you evaluate this?
Right. So we will come to that. So you don't know the true risk that causes the problems. But in theory, I care about these quantities. So all these, what I'm showing now, that I care about these quantities. And in theory, we will analyze how our algorithms converge to the true risks. So these are just theoretical quantities at this point. Okay, there's another question people care about, which is called probably approximately correct, or PEC learning framework, which says that after you define the function class f, your learning algorithm produces this f star n. So this is the empirical risk minimization in this predefined function class f. And what you care about is this question, that you want to find n large enough, so your training set should be large enough, such that the probability that the risk, true risk of the function your algorithm produces minus the best risk achievable in this predefined function class, the probability that this difference is larger than epsilon, it should be smaller than delta, but you fix epsilon and delta. Right? So the question you study, you fix a small enough epsilon and a small enough delta, and you ask the question, how large my training set, how large it should be, that if I do empirical risk minimization, then the true risk of the function my algorithm produces is not too far than the best achievable risk in this function class f.
If for every epsilon delta you have an n such that that holds, then your estimation and it converges to certain probability.
Right. So you, if this is true that for every epsilon and delta there's an n, then you can prove that the estimation error is going to 0 in distribution. But yeah, sorry, in probability. Yeah. Okay, so that's the PEC framework. If you see some papers on that, this is what, and there are like conferences on this framework. All right, so there's this. The first issue is that f should be large enough that the best risk in the function class f should be close to the base risk. And the second issue is that after I fix my function class f, somehow I want to solve this minimization problem easily. So you fix the function class f, and then you need to minimize over all possible functions in that function class f. You have to solve this minimization problem. If it's difficult, then it doesn't help your life much. So one approach people do is two things you can do. Choose the function classes wisely. Or second thing you can do, that choose your loss function wisely. So for example, if we consider the 0-1 loss, that's not a convex loss, we learned that. But because of that, sometimes people replace this loss with hinge loss, and then at least the problem would be convex for you. Does it make sense? So if you, depending on your loss function you use, your problem can be either convex or not convex. If you just have the 0-1 loss, then your problem wouldn't be convex. What we did in, say, support vector machines, that we replaced the 0-1 loss with hinge loss, right? And then at least this problem will be convex for you. Okay, so this is just a big picture demonstration of what we want to do. That our goal is, from the training set, the algorithm should learn a function f star n such that its risk is as close to the base risk as possible. So in this area, here is all possible functions. So say we are solving a classification problem, that I consider all possible functions that map my input domains to 0-1 class labels. That's this area. On this area, if I minimize the risk, then that would be the base risk R star. I also define a function set f, that's here. And I can talk about the risk of those functions that are in this set. And in this point, say that's the point that minimizes the risk in this area. That's called R star f. And my algorithm produces f star nf, that's this point. And we care about this distance here, how far is the base risk from the risk of that function that my algorithm produces. And I just decompose this as the sum of two terms, the approximation error and the estimation error. And I want both of these terms to be as small as possible. Any questions? Okay, so this is what happens in practice, that say this axis is the complexity of the functions you consider. So you might think of this, that here these functions are getting larger and larger, then the complexity you consider, they are increasing. For any function f, that function has a true risk. Your algorithm doesn't have access to the true risk, but it has a true risk. And usually the true risk is decreasing as you, so we do empirical risk minimization. The true risk of this function that your empirical risk minimizer is decreasing at some point. But at some point, as you consider more and more complicated model, then the true risk, as we discussed, that is increasing. The empirical risk, however, is always decreasing, right? If you consider more and more complex models, then the empirical risk will be smaller and smaller. And this is just the definition of, so this is the point where the true risk is minimum. Below that, we say that the algorithm is underfitting. Above this, we say that the algorithm is overfitting. Right, and if you consider these complicated models, then here at this range, the empirical risk is not a good indicator of the true risk anymore. Okay, so that was just the introduction of risk, empirical risk minimization, PEC framework. And now let's see how to use that in practice for classification. So from now on, we will consider only classification loss. So this framework that we discussed can be considered for any losses. But from now on, we will just consider classification. Okay, and we will consider this loss, the classification loss. Okay, so the loss is 1 if y is not f of x and 0 otherwise. Again, the base risk is the minimum of the true risk over all possible functions. Because our loss is the 0, 1 loss, the risk is the expected loss. That's just the probability of that y is not f of x. F star is that function that achieves the base risk. So f star is the arg min or inf of where you take the minimization over all possible functions and you minimize the risk. Okay, so you minimize the risk, that's probability by is not f of x over all possible functions. And for any function f, the probability that y is not f of f star x, so the base risk, is smaller than the risk of that function f. So this is trivial because this is just the minimum of this for all possible functions. But what's not trivial is this lemma here, that actually in this classification loss, you can calculate the best f star, the best classifier algorithm. And that classifier algorithm will have this form, that you can prove that, let f star, the predicted class label will be 1, if the expected value of y given x is bigger than 1/2, and let it be 0 if the expected value of class label is 1 given x is less than 1/2. So when you use classification loss, then we know how the best classifier looks like in theory. Of course, we still don't have access to this because we don't know this conditional expectation. But at least we know that in theory, you cannot do better than this. That's the possible classifier that in theory you could achieve. And it sounds reasonable, right? That you calculate the expectation of the class label condition on X. If it's bigger than half, then let's say that it belongs to class label 1. If it's less than half, then let's say it belongs to class 0. Right? So it makes sense. The proof of this actually is pretty complicated. So we are not going to prove it, but at least you should know that when you use classification loss, the best classifier should have this form. That achieves the base risk. Questions? All right. So here is the thing that now we will need lots of definitions, and I wrote them here, and I would like you to copy these ones. At least you should know all these notations because we will use them in the next lecture and this time, in the next 10 minutes. Okay, so what are these notations? So the risk of function f is just the probability that y is not f of x. So that's the risk of f. The empirical risk of f is just the empirical average of the losses. The base risk for a classifier is that the minimum of the risks are defined by this, over all possible functions. The risk, true risk of in a function class f is the risk of a function f star f, where this f star f is just the argmin of the risk in this function class f. We can calculate the empirical risk in this function class f as well. So what you can do is that so for each function f, you can calculate its empirical risk, and we can minimize these empirical risks in this function class f. That will be denoted with this r hat star and f. So f star and f is your empirical risk minimizer that minimizes the empirical risks in this function class f. Okay, so this is the point where we should stop if you don't understand these definitions, otherwise you will be lost forever. So any questions about these notations? Yes?
So in the second column, the first definition, shouldn't f be from x to 0, 1?
So this should be 0, 1, right?
Yeah, because we have classification.
Sure, yes. It doesn't matter because we consider all possible functions, but yes, just let's assume it's 0, 1. Any other questions? So it's a good point. So that could be 0, 1. Okay, so from now on, if I use these notations, it will be clear what I mean on them. Okay, so again, R of f, that's the risk of f. R star is the base risk. F star is the base classifier. Base classifier is that classifier that achieves the base risk. So that's, in theory, we know it has this form. So that's called base classifier. It has no relationship at all to base rule, but it's just called base classifier. And f star and f is the classifier that your empirical risk minimizer produces when you minimize in the function class f. Okay? Okay, there's an interesting theorem that we will need. Is so there's a true risk that's the best possible risk achievable in this function class f, that's r star f, there's a true risk of the function that your algorithm produces. And we can prove that the difference between these two quantities, so this is a true risk, this is a true risk, this is that you could get the best possible classifier in the function class f. This is that the function that your algorithm produces. This difference is less than 2 times the subprimum over this. So r hat n f is the empirical risk of a function f, and r of f is the true risk. So the point is that if I want to bound this quantity, then I just need to bound this quantity here. So why I care about this? So my algorithm produces a function, f star nf. I want to know how far its risk, true risk, how far is this true risk is from the best possible risk in this function class f. And it turns out that I can bound this quantity with this expression here. Okay, and there's another theorem that we need, is that, so again, my algorithm produces f star nf, the empirical risk minimizer. It has an empirical risk. I can calculate the empirical risk. And we can prove that the empirical risk of this function minus the true risk of this function is less than this quantity. It's pretty trivial because f star n of f is a member of this function class f. Anyhow, again, we can use this same quantity here to upper bound this quantity. All right, so the two theorems we have. So the true risk of f star and f, so the empirical risk minimizer, the true risk of that, minus the true best possible risk in function class f. This is less than 2 times supremum or function in this function class f. The empirical risk of function f minus the true risk of function f. So that's theorem 1. And theorem 2 is the empirical risk of the function that my algorithm produces. So the algorithm produces f star nf function. I can calculate its empirical risk, that's this quantity, minus the true risk that I cannot calculate of the same function. Can be upper bounded exactly with this quantity here, except we don't have this too. Okay, and the corollary, if you put this together with the triangle inequality, then you can say that my algorithm produces f star and f, the empirical risk minimizer algorithm. I can calculate its empirical risk. This would be the best possible risk achievable in this function class f. I cannot calculate this. And this quantity here can be upper bounded with 2 plus 1 times this supremum. So if I can bound this quantity here, then I will know how far the risk that the algorithm produces how far is the best achievable risk in the function class F.
I want to check whether whatever these two equations, whether it will be related to the graph that you have shown us earlier. Like several slides ago, there is a triangle actually.
Mm-hmm. Yes,
So
yes.
using the same triangle inequality.
Okay, so
Is that right?
This one, right?
This one.
Right. So this time, I just care about this. So I even decompose this one to two more terms, and I don't care about this guy.
I see.
Okay, so we just focus on the estimation error this time. Okay, so this F is fixed. If you care about this, then you need to increase the function class F to get larger and larger, and then the minimum risk in the function class F would converge to the minimum risk among all functions. Okay, so what we are doing now, we just decompose this even further.
So you want to bound this with
We bound the estimation error. Okay, so the algorithm again produces this function. Okay, so let me come back to this. Actually, this is a bound on the estimation error, right? So times this supremum. The issue is that, so the algorithm produces this F star and F. You don't know these quantities, but right. So this is the estimation error, and we can bound with this quantity. So if we can somehow estimate this quantity, then you will have a bound on the estimation error.
You can't necessarily compute this. You always say the algorithm creates this.
So which term you are talking about?
This one, yeah. I mean,
This one?
It's not just fn star.
So I can calculate this.
It's not something you may be able to compute, maybe not. This is just something.
So let's assume.
Will minimize your risk on your data.
Right. So let's assume that. Right. So let's assume that. This is that the algorithm produces. So let's assume that the algorithm. Oops. So let's come back here. So my algorithm produces this quantity F star and F. It has a risk. I cannot calculate the risk of this, but
even this function you may not be able to find. I mean, you just assume that you have it. But not necessarily you have an algorithm that can find this function.
So let's assume let's assume that we found this. Okay, so let's just assume that you were able to perform this empirical risk minimization. Okay, and then the algorithm produced this guy. Okay, and then we have this function. Okay, but you are right. If you cannot even calculate this, then our life would be even more complicated. But so I want to avoid discussing the computational complexity, so let's just focus on the statistical properties. So I assume that this function is known. So I know this function, I just don't know its risk. All right, so I want to finish here. I just want to sum up what we did. Right, so we have these two theorems, and from this it follows that your algorithm produces this quantity. I can calculate its empirical risk. This would be the true risk in this function class F. And I can upper bound this expression with this. So I can also upper bound the estimation error just with this quantity. So from now on, we will just follow bounding this quantity. All right, and this is just another, and I will close with this, just another illustration of what we do. So this is the function class. Each point is a function in this function class that you defined, F. For each point, it has a true risk, that's the red curve. For each point, it has an empirical risk as well, that's the green curve. We can calculate where is the biggest difference between these guys, that's epsilon. And these quantities that we just discussed, this is 2 epsilon, and this was upper bounded with epsilon. And right, and so f star f, that's the minimum of the true risk in this function class. So that's this point here. F star nf, that's the minimum of the empirical risk. That's this point here. And if I care about the estimation error, say this quantity, this theorem just says that the estimation error, that is the risk of f star nf, so the true risk, that's this, risk of f star nf, minus the risk of f star f, that's this quantity. So this difference here is less than 2 epsilon. Can you follow this? Again, so this is the true risk. This is the empirical risk. Epsilon is the biggest deviation between the true risk and the empirical risk pointwise for each function f. If I want to bound the estimation error, say this quantity here, then the theorem says that the estimation error can be bounded with 2 epsilon.
And the epsilon, we don't have.
No. So this is where we are. So next time, we will continue bounding these quantities even further. Okay, I'm just saying that if you want to bound your estimation error, you can upper bound with this quantity. And from what follows, we will even further bound these quantities. Okay, so it's lots of calculations, lots of notations. So please look at the slides by next week, next Monday. And then we will continue from here.